So today I want to talk about computational complexity. And I want to talk about computational complexity both in the classical world and in the quantum world. And I want to explain some of the commonly used language to describe computational complexity. And in the end, I would like to also talk about how to translate a difficult problem in classical setting to a less difficult problem in a quantum setting. So to start with, let's imagine one of the simplest algorithms, adding numbers. And to simplify even further, imagine we're just adding ones. So 1 plus 1 plus 1 plus 1 plus 1. Say I have 5 ones that I want to add. How much effort does that take? How much time does that take? Let's say it takes me 5 units. 5 units of effort, 5 units of time. Now I add another one. How did the time required from me or the effort required just change? Well, it went from 5 units to 6 units. I add another one. How did the time effort change? Well, it went up to 7, right? So you see what's happening. The more ones that I add, the more time I will need to add them, and the more effort I will need to add them. And these algorithms are so-called linear complexity. So the more ones that we add, the more time we need, and the more effort we need. And it's the same for, let's say, multiplication, addition, and all these algorithms where they're sort of simple, right? And they are linear complexity. Now let's look at the second example. You want to color a square. You have a square and you want to color it. And now you double the side of the square. How did the area of the square just change? Well, it quadrupled, right? So if you want to color it, you need 4 times more time. You need 4 times more effort. And you can generalize this, of course. So you take a cube and you want to color the volume of the cube, double the side. What happened is the volume of the cube just increased by 8 times. So the complexity went up by 2 to the power of 3, or the time, the effort went up 2 to the power of 3, and so on. And all these algorithms, sort of linear, quadratic, cubic, etc., these are called polynomial complexity or polynomial time algorithms. And what that means is that they depend, so the complexity, the time, the effort depends on the base parameter polynomial. So linear, square, cube, etc. And these algorithms, they're very nice. And so we can compute them fast, cheap, effectively on classical computers, and we know how to do this well. They can still be very, very complex, very, very expensive to execute, but they're sort of under control. However, a less nice class of problems are problems which are sort of difficult. And difficult has a special label in complexity, and these are typically called NP problems. And NP stands for non-deterministic polynomial. And this concept, I mean, it's a little bit difficult to understand without the mathematical background, but let me try to illustrate this on an example. Let's say you want to travel from point A to point B in a system, in a city. And the way you would do this deterministically is you would go from point A to point B, like going intersection by intersection. So you go first intersection, second, third, fourth, and then so on, and then you get to point B. So, just going down the streets. And then you would change your path a little bit. So you would go from intersections, but you would turn right before that, and then you turn left, and then you get to point B. And what you would do to find the minimum time, the fastest route, is you would go through all such paths, and you would identify the one that takes the least time. That would be a deterministic system. Now, non-deterministic systems, what you would do is you would go from point A to all the intersections at the same time. And then from all of those, you would go to all the next ones, and so on. And then you would compute the time needed and get the best solutions. And these algorithms, I mean, they're very efficient, of course, because you're sort of trying all the options as you go. But they require a very powerful machine to run it. And these machines, they don't exist in nature, by the way. We're not able to construct such machines at all. but they're sort of a tool, theoretical tool to evaluate complexity. Well, and now to return to NP. Well, NP problems are problems which are computable in polynomial time, so linear, square, cubed, etc., on such a machine, which evaluates all the options at each step. And this NP problems, well, P problems, so the polynomial problems, which are like linear, quadratic, cubic in the deterministic machine, right? They're a subset of NP problems. And what we are interested in, or sort of what the interesting set of problems for quantum computation is problems which are NP, but are not P. So problems which are polynomial for a non-deterministic machine, but are not polynomial for deterministic machines. And there's a lot of those. So factorization, for example, of large numbers, even traveling salesman problems, so problems in logistics, problems in cryptography, they're all problems which are not polynomial on a deterministic machine, but they're polynomial on a non-deterministic machine. And now going to quantum, so the way quantum works, right, the structure of quantum is sort of somewhere in the middle. It's between a deterministic machine and a non-deterministic machine, because we have these particles, this qubit, the quantum bits, which are connected to each other through entanglement. And this entanglement sort of allows us to have more and more states at each step of entanglement, right? The more we entangle qubits, the more states we are sort of building. And this allows us to sort of model this behavior of the non-deterministic system to go and evaluate all the nodes simultaneously. Just to be very clear, quantum computers are nowhere near as powerful as non-deterministic computation machines. But they are sort of different in a way that they process data compared to deterministic ones. Right. So by the way, we also have a set of polynomial problems, so problems which are solved in polynomial time in quantum computing, and this set is often called BQP, which means bounded error, quantum, and polynomial time. So these are problems which are solved in polynomial time on quantum computers. And so the goal right now is to find problems which are not polynomial on deterministic machines, because those we can solve well on classical computers. But they're polynomial on non-deterministic machines, and at the same time, they're polynomial on quantum machines. So we're going from problems which are non-polynomial on deterministic computers to problems which are polynomial on quantum computers. And in this way, we can sort of speed up the computation, we can reduce the effort needed, reduce the time, reduce the energy consumption, reduce the money. And there has been great success, especially in the areas of a large number factorization, cryptography, etc., but also other problems like traveling salesman problems in logistics, problems in optimization, of translating these problems which are not polynomial on deterministic computers to problems which are polynomial on quantum computers. And we're working on finding more of these problems which can be translated well and solved efficiently on quantum computers. And we hope to make a lot of progress in this direction in the near future as well.